I'm saying something right now. Hello everyone. Should I get started? Yes. Yeah, awesome. All right, thank you, sorry about that. Well, I guess it's 2,000 crowns, 2 days of conference, including breakfast and lunch, and there's a bunch of intelligent, smart, funny, interesting people coming to talk, and there's also going to be open spaces. We're also going to make sure that there's a discount code for everyone that's attending this meetup for 20% off. I'm going to ask you to send it out to you after the meetup today. So I hope to see as many as possible. We have probably around 200 tickets left, so please join. Thank you very much.
Okay, I'll take over now. My name is Björn. In this country, it's fortunately not an exotic name. It's very hard to explain to new speakers. I'm visiting here from Berlin. I'm probably the most, like the earliest Prometheus contributor in the room, I think. That's probably why I have to speak now. So we have taken over this meetup, rebranded as the Prometheus meetup. I think we're about 70 people in the room. That might be the largest dedicated Prometheus meetup ever. Tom, Tom lives in this mid-sized city in Great Britain where they also have a Prometheus meetup. Yeah, okay, so we are more than 60 definitely. I quickly counted. Okay, great. Greatest, biggest meetup of Prometheus in the world. We have we have probably loads of Prometheus contributors here. It's an open source project, but we have a governance structure in the project, and there's a voting body, which is called Prometheus Team, and it has like 20 people in it, and 4 of them are in the room, which is Tom from this small town in Great Britain. And then we have Ganesh. And then we have Goutham here, who will give a talk in a second, and then myself, Björn. Cool. Is there anything more to say? No, right? Goutham will just take over and talk about, hey, Prometheus, what's up? I think this is about new stuff in Prometheus recently, right? Okay, you can take over. I think you have to. Yep. Do you want to keep it, or we can wire you up?
Can you hear me? How about now? Can you hear me? Okay. Yeah, I'm going to talk about Prometheus, what's new, what's happening. I'm Goutham. I am a developer from India, and I've been working on the Prometheus project for about 2.5 years now while still in college. How many of you are aware of the GSOC program or Google Summer of Code? Yeah. I got into Prometheus via the Google Summer of Code, and then I kept contributing, and now I'm a Prometheus team member. Wow. Yeah. First of all, most of these slides are from an amazing talk given by Björn at DevOpsCon. I just updated them. It's just a month or 2 old, so it's mostly relevant. And yeah, we're going to talk about Prometheus. So, how many of you use Prometheus? Okay, how many of you don't use Prometheus? Ooh, why not? Yeah, so for those of you who don't know what Prometheus is, it's the world's best monitoring system. Use it. It's a really good monitoring system. It's open source. It's super simple to operate, and it has got immense adoption. For those of you in the Kubernetes or cloud native world, it's like the de facto monitoring system. And a little bit of history. Yeah, The first commit is almost 7 years old, so it's been a long time, and it was actually started in SoundCloud. So in 2012, a bunch of ex-Googlers went from Google to a startup, and everything was on fire, and they're like, where's my monitoring? For any ex-Googlers here? Oh wow, if you're an ex-Googler, you will be familiar with this monitoring system called Borg, which is amazing, and they come out into the real world and they're like, oh no, I don't have any of my tools. So ex-Googlers being ex-Googlers, they just built one in the open source world, called it Prometheus. And it was always open source. The amazing thing about this is SoundCloud is a music company. They didn't actually care about a monitoring system, so they let it be open source. It was open source from scratch, and people are developing it in their 20% time. And in 2015, after adopting it at SoundCloud at scale, they announced it in a blog post. So this is like the first public blog post, and you can probably say this is when the growth started, the adoption started. It was 2015. More than 4 years, nearly 5 years. And then in 2016, we joined the CNCF after Kubernetes. How many of you know what CNCF is? Okay, for those of you who don't know what CNCF is, it's a foundation that hosts all these open source projects in the cloud native containers Kubernetes space, and it was created by for hosting Kubernetes, and then they added Prometheus. And it was not even 1.0 back then, even though it's under development since 2012. It only reached 1.0 in 2016 after it joined the CNCF. And then a year and 2 months later, we released Prometheus 2.0. So those of you who are using Prometheus, how many of you are still in some version of 1.x? Wow. It's still amazing. It still works. Yeah. Yeah. And then we launched Prometheus. Oh, nice. Yeah, and then we went back. We were like, okay, we built something, and a lot of people are using it. Let's look at the common problems being faced. Let's look at all the mistakes or like the issues we are facing, and let's like fix all of them. And that's what we did. And it's been nearly 2 years since we did 2.0, and we're still on 2.10 because anything we wanted to fix, we almost all fixed it in 2.0. And then we graduated in CNCF. How many of you know what graduation in CNCF means? For those of you who don't know what graduation means bye-bye, you can leave. But no, that's not what it means. Graduation means this is stable, this has been used in production. You can confidently use it in production. We recommend that you run this in production. It's been through a lot of development, and it's stable now. That's what graduation means. But what does it mean for us as a project? Like, what does being a graduated project in CNCF mean? Absolutely nothing changed. In fact, our activity increased. So this is like 2015. People are doing it in the 20% time, and then we announced it. We got shit ton of adoption and contributions. This is the Prometheus GitHub activity as a chart, as a Grafana dashboard. And this is, you can see, this is when the graduation happened. And the activity like increased or probably even doubled, and it's consistently like, it's still a lot of innovation happening in Prometheus and in the ecosystem now. Like, it's still going good. And yeah, this is the simple architecture of Prometheus. Looks very simple, right? But the good thing is, all of this is a single binary. Like the Prometheus server that you see is just a binary. You just download it, /Prometheus, and it works. Internally, what we do is we actually, for those of you who are not familiar with the Prometheus model, I'm just going to quickly run through it. So Prometheus has a set of targets it monitors. No target sends metrics to Prometheus. Prometheus goes and asks the target, hey, target, give me your metrics via HTTP request. Those are the jobs or Prometheus targets, and it gets this HTTP page, which it ingests as metrics, stores it in TSDB, which is the ingrown, home-built time series database, which is amazing because I'm one of the maintainers. And then you have a UI to kind of look at Prometheus. There's a default UI, there's Grafana, and you also have alerting on top. So once you have all this data, you can write an alert saying, if my 500 errors are more than 1% for 5 minutes, send me an alert. So Prometheus gives you the end-to-end monitoring, like monitoring, alerting, and dashboarding via Grafana. It's a monitoring system. It does have a time series database, but it's a monitoring system. Yep. So we've been in development since, what, 2012. And here I'm going to introduce you to what's new. If you're stuck in a version that's 1.x, please upgrade, and here's what's new. But yeah, let's see what less than 1 year old means. First, I want to deal with the release schedule. So initially, before the schedule was created, we just used to release when we saw fit, and that's not good enough. Sometimes we were not releasing for 3 months, and there were like a lot of features, a lot of bugs that are piling up that nobody's testing. So now we have a release cadence, where we cut a release, release candidate every 6 weeks, and then you can go test this candidate in your local environment. But yeah, let's see what 1 year means. It's everything after 2.4 when this release doc was created. Yeah, we're going to talk about all the features that happened since 2.4, which is just 1 year, but there's a bunch of releases. And the other good thing is, all this activity that you've seen that blew up came from new contributors or new maintainers. We've added 5 new maintainers in the last year. Now we have 20, and there are tons more we want to add because they're super active. Like the project health is amazingly good. Yeah. The other good thing is 4 out of these 5 people are being paid to work on Prometheus and the ecosystem. Before this, I think majority of the maintainers were doing it in their 20% time, but because of all the activity, the adoption, and all the opportunity that is there in the Prometheus community and ecosystem, people are investing actual dollars into the ecosystem, sustaining the project. Yeah. So I actually gave a variant of this talk at GrafanaCon this year, and so it has some details, it has some new features that are not there in Beyond slides or this new slides. You can always go back and watch the talk. Actually, Beyond apparently likes my talk better than his talk. Yep. So one of the things we have in alerting that a lot of people like is the 4 state. So you will have spikes, but you don't want to be paged or woken up when you have a spike of errors, because like there's something happened, some node restarted, there's a spike for 1 minute, but your system healed and everything's back to normal. But because of this 1 minute, you were woken up at 3 AM in the night. So you don't want to have these spikes alerting you. You don't want to write an alert that says, if my error rate is more than 1%, send me an alert. You want to be like, okay, if my error rate is more than 1% for 5 minutes or for 15 minutes, then send me an alert. So there's this 4 period that kind of stores how long this alert is active, and then and then notifies you if it's long enough. But the problem is, sometimes people are like, okay, this is a database, the disk can fill up for like 3 hours, and maybe we can cope up for 3 hours, or probably there's a compaction that's running in a database that runs for 6 hours, taking up disk. But if it's running for more than 6 hours, then send me an alert. So this 6 hours is a long period. Some people have this 4 period for days, and when Prometheus restarts, we would totally forget about this. What would happen is, if alert is active for 23 hours, you have a 24-hour period, Prometheus restarts, you need to wait 24 hours more, which is useless. But that was like one of the nuances, one of the painful parts of Prometheus, and this was actually fixed in 2.4, and this is like an issue open from 2014. And when I say this is painful, and you're like, okay, that doesn't seem too important, you can kind of see how stable Prometheus is already by that point, by a year ago. And by the way, this was implemented by Ganesh as part of his GSOC. GSOC is amazing. We've been getting a lot of maintainers, contributors through GSOC, and they're like super high quality content. Yep. Yeah. So this is the other thing. Because of Prometheus's model, we used to have a retention period based on time. We can only say, hey, delete, I only want to store 15 days of data. I only want to store 30 days of data. But that's not how disks work. You have a 1 TB disk, and you want to store 900 GB of data, not 15 days. And even if you configure something for 15 days, your usage might grow and your disk might give up. you want to have some kind of a disk-based or like space-based retention. That was another one of the other big asks. We don't think it's a good idea, but we still implemented it because you want to have a constant amount of metrics in the time. And the other thing that was painful is when you issue a huge query, Prometheus used to crash. Prometheus used to consume a lot of memory and it used to crash. Like the number one Prometheus crashing scenario was issuing a huge query. Like nothing, it was super stable at that point. So we wanted to fix both of them, and we did. Yeah. So this is also, I think this is like, at that point when we were fixing it, the second or like the oldest issue that was open. And yeah, so after 273 comments and reviews on this one PR, because it's hard to do, like it's kind of hard to figure out what to delete, what not to delete. Should we delete on time, should we delete on space, how to do it easily, how to make it testable, because you know you're deleting files, creating files and all of that. Yeah, after 273 review comments, we finally got this merged and it works really well. So for those of you who don't know that this exists, you can go back and configure your Prometheus to say, hold data for at most 30 days or at most 500 GB. So if your usage grows, your Prometheus still won't go down. Yeah. This happened quite recently, recently as in 2.7, we are at 2.12, which means 30 weeks ago, recently. Yeah, we changed our flag. Initially, we just used to say retention is 15 days, retention is 30 days. Now you can say retention.time is 15 days, retention.space is size is x GB. Yep. Yeah, in Prometheus 1, when you were trying to ingest too much, it used to crash. So we used to have this flag that says if my Prometheus usage is more than 15 GB or whatever configurable limit you had, use less memory. We could tell Prometheus to use less memory, and it used to try its best to use less memory, and that actually saved a lot of people a lot of crashes. But when we redesigned that, because of how the storage engine works, we kind of couldn't make it easy, so we just left it out. And Prometheus 2 is stable, everything, but it used to crash when you send huge queries. And we wanted to fix that. We are not happy, like, and yeah, Tom and Callum, again, who are here, you can speak to them. They've implemented this max samples and yeah, max sample. So the main issue with Prometheus ooming is when it tries to query data, it can load all the data into memory from disk, and there's no way to limit this amount of samples. And this is actually not an easy task because you need to instrument the query engine to see what samples are in memory, what samples were in memory. Like, so you have to do like a lot of addition and subtraction based on what data is in memory. And I think even this took like more than 150 comments. And Callum, yeah, he knows, he's nodding, had to patiently work through that. But finally, you can stop your Prometheus from ooming now. You can set all these values to make sure that your Prometheus doesn't take up all the memory. Yep. How many of you understand what subqueries are? Subqueries are fairly recent. Okay, how many of you can guess what subqueries are? No, for those of you who don't know what subqueries are. So, yeah, you can. Yes, the example will make it super clear. So this was painful, and yeah, I'll tell you what it does. Yeah. So basically, you want to look at the rate of the samples that you're ingesting over the last 1 hour. You want to take a rate of every 5 minutes. You want to look at the rate for 1 hour, and you want to look at the max rate in this 1 hour. And that's what this query tries to do. For those of you who are familiar with PromQL, max over time over 1 hour for a rate that's in the 5-minute window. So essentially, every 5 minutes, what is this rate? In the last 5 minutes, there are 12 rates, and in this, what is the top? That is what we want to achieve, and that's not possible. And that was like, this was the error that used to come up, and because it was kind of hard to solve this problem, because you might use too much memory, it was super inefficient to do it. And then in Prometheus, initial versions of Prometheus 2.0, we made the initial changes in the query engine to make this easy, and now it's possible to do it. you can say, you can just put a column there and it just works. But what's happening there? So the problem with this, forget the inefficiency. You have a rate over 5-minute window, and then you have the 1 hour, which you need to do max over. But how many, like 5-minute window could be like every 1 minute in the last 5-minute window, or every 2 minutes in the last 5-minute window, or every 5 minutes. Like how frequently do you want this rate? How do you express this? So that was the problem. How do you create another time series from this rate instead of a single value? And what this column does is it gives it an interval. And by default, I think it's 1 minute. If you put just a column, it will just calculate the rate over every 1 minute. It will have 60 rates, and it will take the max. But you can also specify, I want rate over every 5 minutes or 10 minutes in the, like after the column, 1 hour, 1h column, 10 minutes, and then you'll have 6 rates, and you can get the max. So this is like an advanced use case. But when people really needed something like this, we're like, yeah, make a recording rule. And they're like, no, I want to look at the past data, and recording rules don't do past data. So we didn't have a good solution for this, and now we do. It might not be super fast, but it's still extremely fast. And for those who are completely confused by this, there's a blog post. You can just Google subqueries in Prometheus, and it works. And this was like beginning of this year. Yeah. Oh yeah. So how many of you have looked at the roadmap for Prometheus? So the roadmap for Prometheus is public. You just Google Prometheus roadmap, and we have like 4 points here. One of them is server-side metric metadata support. So you kind of want to know if this. So how many of you looked at a metrics page? So I said Prometheus sends a HTTP request to get the data. But what does this data look like? Can you send the HTTP request yourself to look at the data? Yes, you can. How many of you have tried it? Good. For those of you who didn't, I want to show you that. Let me see if this works. Yeah. So this is how it looks. Let me just make it big. So you have the help text, the type text, and then you have the actual metric. And this is the actual metric being exposed by that service. A lot of people use this page to debug things when they're on fire. They're like, okay, this service, it doesn't look right. Let me see what it's exposing. And sometimes you're like, this makes no sense. Prometheus is messing up. I don't trust Prometheus. And then you go and you see this, oh, Prometheus is right. My service is messing up. But you know, this page actually helps you understand what the type information is. Is it a counter? Is it a gauge? Is it a summary? And like it has this help explanation. And there's no way you could query this data inside Prometheus. You're querying something, or your coworker wrote a query. You're like, okay, what is this weird metric called log messages 500 MB total? What does this mean? You can now actually query the data from inside Prometheus to get that. Yeah, and it's been there since a year. This has been implemented. You can kind of go to you can use this API. We still haven't figured out how to put it into the UI itself, but we will soon put it. Like if you have a query, we will tell you what metrics that query contains and like what's the help text is, so you can understand what's happening. But right now we have an API that can retrieve this data help and type information for you, making it easier to debug. How many of you know what open metrics is? Okay, yeah, open metrics is a new standard, but why do we need another standard? But the thing is, a lot of people, how many of you have tried InfluxDB or like OpenTSDB or Graphite or some other monitoring system? Oh, I'm surprised. A lot of you started with Prometheus, which is amazing, by the way. But so people want to move from Prometheus to another monitoring system, or from another monitoring system to Prometheus. But then they find that it's not actually as simple as changing the server. Oh, I just want to remove this old monitoring system and I want to install Prometheus. It doesn't work like that. You have to go back to your code, change all the lines where you said expose this metric, increment this counter. You have to change all these lines. to make it work with Prometheus. And then if you want to move from Prometheus to something better, you have to go back to your code, change all those lines to make it work with the new system. And that was like, that is lock-in. And we want to avoid that. We want to help people move to Prometheus. And we are also nice citizens. If somebody wants to use something else, we want to make that happen. And how many of you think SNMP is fun? Yeah, so we have a bunch of network guys. One of them is like leading this open metrics project. He hates SNMP, but that's the only way you can monitor network data, right? So by making it a new standard, an IETF standard, he's just gonna say, oh, you're in this tender, in this contract, your device also needs to support open metrics. And he hopes that the vendors will do it, and he can kill SNMP forever. Yeah. Yeah, so there's open metrics. This is a new standard. It's also part of the CNCF. It uses both text and protocol buffers. It's super efficient. It's amazing. It's coming soon. But what does soon mean? I think we have support for it in Prometheus itself, and we also have support for it in the client. Like if you have a Python app, you can actually use open metrics today. And we're going to just add support. We're also going to use the existing code that you have. You just update the version of client Go or like your client Python from 1.x to 2.0 or something, and you just get open metrics for free. Which means you can move your existing Prometheus move from your Prometheus monitoring system to this new shiny monitoring system, which also supports open metrics, just by one configuration change. Makes things simple. Yep. How many of you want this? Backfilling of time series data. Yeah, I know everyone wants it. Yeah. So what does this mean? So essentially, you have your existing monitoring system. You have 5 years of data in it, and then you go to Prometheus and it's like, how do I move this data from this old monitoring system into Prometheus? Or you suddenly discover that there's someone else having some interesting data that you want to correlate with the data inside Prometheus. How do I put this data back into Prometheus so I can run some queries? Like, backfill has a lot of advantages, and a lot of people want it. And right now it's actually, yeah, I talk about this in detail. Ganesh is going to talk about it later. But it's actually possible in 2.8, which is kind of recent, one of the recent things. Yeah, I just want to leave it to Ganesh because he implemented it. And the final thing in the roadmap is TLS and authentication in HTTP serving endpoints. So we went through a security audit, sponsored by the CNCF. Like, it was good, and we nothing. Prometheus is great because I'm one of the maintainers. Nothing was wrong with it. But they did say, hey, there's no way to authenticate the exporters or the jobs. Like, essentially anybody can access the job. Prometheus can access job. I just want my Prometheus from team A to scrape only my things. Like, there's no way of this authentication that is built in to the client libraries or the exporters or the jobs. And we are like, yeah, I know, you need to run a reverse proxy. You just put Nginx in front of it, do your things in there, which is not acceptable. We thought it was, but it's not, we know. And enterprises are requesting it, and this is the only thing that is in this list that is not implemented yet. Having said that, look at how many, yeah, okay, there's like 29 commits and 114 reviews, because TLS is hard. And we want to get it right once for node exporter, and once we have that, it will be a library that all the Prometheus components will use. And suppose there's a vulnerability in TLS, how do we update things across the board? All of them, we need to do a bunch of releases and all of that. So TLS is hard, we want to get it right, and a lot of people have a lot of opinions. And the good thing is, this person is like Callum and the other guy, very patient, and I saw the last update was 24 hours ago. So it's almost there. So soon you'll be able to authenticate your services or your jobs and make sure only the right people can access it. And so that's it. Yeah, this is like the end of the roadmap. So what do we do now? Do we all go home? Is Prometheus done? Not really. So we actually have this yearly dev summit where all of us get into a room and discuss what to do next. And we have a lot of exciting things. You can actually Google Prometheus Dev Summit notes, and you can see what we have. And one of the things I'm excited about because I have to implement it is exemplars. How many of you know what exemplars are? So the thing is, you know that how many of you know about tracing and distributed tracing, Jaeger? Yeah, most of you know what distributed tracing is. Now we have all these metrics, right, from your services that say, okay, there's a spike of 99 percentile latency, just spike to 5 seconds. And you want to look at a trace at that moment, probably a trace that was at 5 seconds. There's no way you can directly jump from Prometheus to your distributed tracing data. And we are now exemplars are this example traces for that 5-second bucket, for that 3-second bucket. So essentially, when you see a spike in Grafana or in Prometheus itself, we'll show a nice star saying, okay, this is the spike. And you click on that star, you go to this 5-second trace in Jaeger. So this way you can quickly debug things when things are slow or when things are super fast. This request should take 5 seconds. Why is it done in 5 milliseconds? Is it doing any work? What's happening there? So you can do all of that. And yeah, you can, I think I'm done. Yeah. Hmm? Yeah.
Yeah, so we have a few minutes for Q&A. You can ask Goutham anything. We can also jump in, but we'll also have 30 minutes mingling later where you can ask all of us. But first, you have some immediate questions. You look like you have immediate questions.
I think, yeah, so the question is, now that we fixed the oldest bug, what's the next oldest bug? A modern UI, if I had to guess. And funnily enough, it's almost there. The weird thing is we're using the JavaScript ecosystem, and npm install brings in a ton of code, and we need to figure out licensing and all of that inside that ton of code, packaging that efficiently and all of that. But it's almost there. You're going to have a fancy React UI that auto refreshes.
You can go to the
GitHub.
page and just check it out, but I think the oldest ones are really high-level bugs that are almost like roadmap items.
Yeah.
So they are not really this one feature. It's more hey, you can check it out.
Yeah.
Not really bugs. It's more goals.
Yeah.
Okay. Any other questions? There.
What's the first one? Flap detection. Yeah. Yep. So the question is, what are your ideas about flap detection and handling of alerts? Yeah. So yeah, flapping alerts and acknowledging alerts. So the idea is you get a notification and you need to act on it. You need to be like, okay, I'm working on it. If I don't resolve this alert in 30 minutes, send me another alert. Remind me. We think all of this is the job of an external system, like Victrops, PagerDuty, or like LinkedIn Iris. But what we do want to improve is alert history. So if you have the alert manager, it will tell you what alerts are firing now. It won't tell you what alerts fired 5 minutes ago, or it won't tell you, okay, these are the top 3 alerts and they fired 35 times in 1 hour. You probably shouldn't alert on them. Like, there's no way we don't have this history. And one of the projects that we have in mind next in the ecosystem, not in the core Prometheus core, is this alert history where you can see what alerts fired when and how many fired and all of that. Mm-hmm. Mm-hmm. Yeah. This requires a longer discussion, and it's mostly use case specific, so we can discuss it offline.
By the way, there is an item about that in the latest F summit.
Yeah.
It's like keyword is automator, it's like issue management, issue tracking. It's kind of outside of Prometheus' scope right now, but there are activities to do something about it.
Yeah.
Yeah, but it's a big topic.
Yeah. Yeah.
Okay, should we take one more? Okay. One more from him.
Thanks for the talk.
Oh yeah, we have a HA setup. The idea is Prometheus is a single binary. It has no dependencies beyond compute and disk. So we don't want to build a distributed system because distributed systems are hard, and when everything breaks, you want your monitoring to work. So our HA system is you run Prometheus 1 and Prometheus 2. Prometheus 1 goes down, you look at Prometheus 2. It's with the Prometheus binary, and both of these are Prometheuses separate. They don't know about each other. They just you collect the data twice. You have 2 copies of the data. They're just like, okay, I'm going to scrape these targets. Yeah, they have the exact same data. Yeah. So we have a HA setup. We have ways of deduplicating and like making sure everything is HA in the core and outside in the ecosystem.
That also leads to a lot of more subtle discussions that
Yeah.
you might have in the break.
Yeah.
Like, don't we go to them?
Yep.
To those people here, they're also crucial for open source.
Yeah.
Okay, let's go to the next speaker. One thing was mentioned most recently in Gotham's
Can everyone hear me? At the back? Hello? 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 1, 2, 3, 4, 5, 6. 1, 1, 2, 3.
That's good. Off you go.
Yep. So hi, I'm Ganesh. So my history with Prometheus goes similar to Gautam. I started contributing 1.5 years ago through GSOC, and now I'm a maintainer of Prometheus, and I mostly work in TSDB, which is the storage engine of Prometheus. So before I dive into what has been improved in TSDB in last 1 year, let's talk about TSDB. So when Prometheus 2.0 was released, the storage engine was entirely rewritten, and it was way more efficient in terms of memory and CPU than 1.x. So if you are still running Prometheus 1.x, it's highly recommended you shift to 2.x. Yeah. Uh, Not recently ago, the TSDB stayed as an independent repo on GitHub, which the Prometheus would import in its code base and use. But recently, TSDB was merged into Prometheus, and it's a subdirectory inside the Prometheus code base itself. And in case if you want to use TSDB in your code base, just like how Cortex, Thanos, and other distributed Prometheus setups do, you can just import the TSDB and it works just like any other package in Go. So the TSDB has very basic functionalities that you just give the time series data, which is just timestamp, value, and the labels associated to it, and then you can query the data. So that's the basic function of TSDB. It handles the compaction and other stuff automatically. Yep. So some statistics about the TSDB. So since 2.0 release, there have been 500 plus commits to the storage engine, and there have been 60 overall contributors. And this was the point when 2.0 was released, and the GitHub has received 771 stars linearly, and it has been growing recently, but now the repo is archived and it's inside the Prometheus. So that's all about the history of TSDB and what it is. Now let's see what has been added in the past 1 year, because it has not stopped in features and enhancements in last 1 year. So let's see what has added. So Gautam mentioned about backfilling, so I'm going to start with that. So the problem previously was that the Prometheus stores data as blocks, and previously it did not allow to have overlapping blocks. For example, if you're going to
backfill the data into the old Prometheus, it's obviously going to be a data which is not in the future but in the past. But Prometheus will just say, no, you cannot have overlapping data, I'll just not start the Prometheus itself. So we had to just have the queries running on overlapping data. So this was added just this beginning of this year, where you could query data on overlapping blocks, and Prometheus will automatically convert them into linear blocks, and it will no longer be overlapping. But this is just in Prometheus. But how can you backfill your the old data into the Prometheus? So Prometheus doesn't have any recommended way yet, but there has been some community effort to get this along. So there is a tool by Julian called Ingest, which was the first step towards getting your data into the Prometheus. But there has been more effort recently. This is still under review, like a tool in which you can give data in TSDB format, and it will just create blocks along with the live Prometheus that you're running, and eventually it will be non-overlapping blocks and you can import your data. So you can still do yourself, but the official support by Prometheus will be coming soon. And let's talk about wall compression. So if you have too many series and lots of ingestion of samples, wall can get right head log can get very big. Does everyone understand what I mean by right head log? Okay, like when Prometheus has two parts in the database, one is in memory and one is on disk. So Prometheus stores 2 hours of data in the memory, and rest of it is stored in the disk. But what happens if Prometheus crashes? Because the 2 hours of data is stored in the memory, that just vanishes away, and if you restart the Prometheus, your 2 hours of data will be gone. But whenever we are getting the samples, we write in something called write ahead log, which is on the disk. So whenever the Prometheus is restarted, the data that you have in the memory is not lost, and you can recover from this write ahead log. But this can soon get very big because of millions of series. And recently Chris, who recently became a Prometheus member too, added the support of having snappy compression. Snappy is compression which is also used in protobuf. Yeah, so it can save up to 50% of your write ahead log disk storage without giving up on performance. So this talk is going to be a little technical, so if you don't understand anything, you can just catch me up later offline. Yeah, and some more optimizations in the write ahead log. This was by another Prometheus maintainer, Brian. I won't go into details what he did, but if you are using some old version of Prometheus 2.0, if you go to the latest version, the wall read time will be like 4 to 6x faster. And yeah, this is regarding the postings. Postings are the Prometheus stores data in blocks, and each block has the actual data and the index of the data. So inside the index, we need to store the reference of the series, and each of those references are called postings. We use 32 bits for each series reference, and that's why we are limited to 64 gigabytes of index. But in large setup, like issue is open on GitHub by Thanos, like they are hitting the limit of 64 GB. And even in large setups where it was just like 8 million series with blocks spanning 9 days of duration, the index can get up to 20 GB, and it was just limited by 32-bit posting. But in the recent GSOC 2019, which I am mentoring, he's Alec Wong from Hong Kong. So the work is towards converting these references from 32 bits to 64 bits without increasing the index size. So we use prefix compression. We just store the prefix and the suffix are just repeated, and we shift to 64 bits. This is still work in progress, and it will be added soon, and hopefully in 2.14 you should be able to have indexes which are bigger than 64 gigabytes. And yeah, and the performance is not affected with this change in posting size. And now I'm going to talk about some allocation and memory improvements in compaction. So does everyone understand compaction? No. Yeah. So when after every 2 hours, Prometheus removes the data from the head, the in-memory what I talked about, and it flushes that into the disk. So each block of Prometheus data is 2 hours long. But if all the blocks are just 2 hours long, there will be too many blocks, and the queries can get slow if there are too many blocks. So in the compaction, we merge the old blocks to form a bigger block. For example, if the oldest block is if there are 3 blocks of 2 hours each, after some time it will be compacted to a big block of 6 hours, which makes the queries efficient. So compactions were one of the things where it just went out of memory because you have to build the new block with all the new index and all the data of the old blocks. So some lots of improvement have been done in this compaction. For example, Brian did a optimization where you don't need to previously we used to have multiple copies of block while compacting, so that you don't use the blocks that is used by the original database. I think this is getting too technical, but yeah, with this the memory used by the compaction goes to half by reusing the blocks that are already open. And recently I was also trying to reduce the memory consumption by streaming the compaction of multiple blocks into a single block. The memory was not reduced, but the byproducts of that were lots of improvement in allocations. I won't go into the details of each allocations. This is just to show the numbers like 35%, 19%, 6.5%. I don't know the number of another optimization. So this was very recent, like July and August. So still the improvement has not stopped and it's going on. And yeah, and now I'm going to talk about improvements in queries. So queries is the storage part of queries is obviously handled by TSDB, and there is a big part of query optimization which is not inside the TSDB. So I'm just going to talk about the TSDB. Yeah, he's the GSOC student whom I'm mentoring. So this is again technical little bit, but I talked about postings, which are the series reference. When you have series reference in multiple blocks and you want to query across multiple blocks, you need to intersect them to if the series X belongs to block 1, block 2 and block 3, and if you get 3 references from 3 blocks, you need to intersect them to become a single series at the end. So we initially used n-log-n algorithm, but he found out that there is another way using n-square algorithm, which is faster apparently in our case. So yeah, this is like 96% faster, 67% faster, and so on. And this optimization is particularly interesting if you're using Grafana. The Grafana dashboard has queries like foo with a regex, bar or buzz. This is just an example. And if you're doing queries using regex, it has to look up all the series because it doesn't know which regex it can match. So for queries specifically like this, which the Grafana dashboards use, it's split into 2 queries, which is foo equals to bar or foo equals to buzz. So this query is much more faster than just using the regex, and with this optimization, which was added just in this May or June, your Grafana dashboard should load up much quicker than before. Yep. And this optimization was added in the recent release. When you're querying, the data is actually stored in format like multiple chunks. Single chunk of data has only 128 samples. So for a query, you need to iterate over all the chunks that the series belongs to. So if you're creating an iterator for each chunk, it gets very expensive. So in this optimization, what I did is use single iterator for each chunk because we are not reading those chunks in parallel. So reuse the iterators. It might feel like it's a very small optimization, but here are the numbers. Like this was run on something called Prometheus, which I'm going to speak about later. So this does some large scale benchmarking on the Prometheus. This benchmark results are comparison between Prometheus 2.11.1 and Prometheus 12. So with this small optimization, there was a huge difference in the allocated space, and even the memory used by lots of gigabytes. You can see this difference only if you are running huge queries on a huge Prometheus server, and if you have a small Prometheus setup, you might not see much difference with this. And also goes the CPU, because allocations, less the allocations, less the garbage collection, and hence the reduction in CPU. Yep. And this read-only mode is particularly interesting if you're writing code to use the live Prometheus TSDB. For example, if you have a running Prometheus, it's not safe to tinker with the live running database because things are being added, things are being removed. So a new interface was added for read-only mode in the Prometheus, which you can use in your code to safely do operations on the TSDB without the risk of harming the data. And I think this is the last thing that I'm going to mention about the features that were added. So Prometheus already has the atomicity, consistency, and durability from these acid properties, but there is no isolation. For example, if you are in between the scrape, it's possible you read some data from the new scrape and some data from the old scrape. So some past work has been done on this from core maintainers Brian and also Goutham, but it was abandoned in between because it was a big PR, and I guess no one wanted to review that big PR. And the plan is to add it again, which is just rebasing that PR on top of the master. There are high chances I might do it, but if no one reviews it, then it's abandoned again. Yeah, so that's about isolation. After this is added, you will have all the ACID properties like all the SQL databases have. And yeah, this is about the Prom bench. Yeah, Prom bench started with the efforts of GSOC students. It was heavily developed upon since last year, and it's led by Krazi, who is another Prometheus maintainer, and most of the GSOC students who come to Prometheus have worked on Prom bench. Like it, started with setting up all the Prom bench, and this year we have 3 GSOC students working on that. So this is just a shout out on Prom bench, which helps benchmark TSDB in a good way. Yeah, that's all. Thank you. Do you have any questions on the storage engine?
We have a few minutes, but then we have mingling time. So
yeah.
Immediate question, please ask now. You ask first. We had no questions so far.
Are there any other projects using the TSDB?
Yes. Yeah, his question was, are there any projects using TSDB? Yes, Cortex uses TSDB, Thanos uses TSDB. Like Thanos is mainly based on the TSDB blocks which Prometheus has. Yep, so distributed Prometheus.
Okay. Regarding isolation, is that requests that you get a lot, and is that something that people have a problem with in the wild?
We have not seen much problem, and it's. Have you seen problem? Yeah. I just know how to implement it, but problems. Yeah. Yeah. Can you tell about isolation?
The histogram problem.
Yeah, but it's.
Ask him
that's
later.
actually fine. I think that's fine, right?
Okay.
Yeah. Well, because that's the topic.
Yeah.
as you can see, there wasn't that urgent, so the work got abandoned, and then perhaps we
It was
pick
cool.
it up again.
It was really interesting to work on that problem.
Yeah.
Yes.
It might be a bit academic, but it's
Yeah.
There are always. I mean, there are now so many users that even bizarre use cases have a certain relevance, and then if it doesn't harm other users, why not implement it? Right. Okay, I think we wrap it up here. We have half an hour break now. We still have drinks and we have food and we have meeting time. Just ask people as you see them. You see now there are Prometheus contributors. Tom wants to tell me something.
And then we're having another talk.
Yes, and after the half an hour we have at least one lightning talk by Tom, who's the fourth Prometheus team member here in the room. And if somebody wants to give another lightning talk spontaneously, just ask me. We will try to make it happen. Okay, now mingle.
No, the microphone doesn't work. Hello? Can you hear me? Is that coming out the speakers? It is, yeah. Right.
Right. Everyone.
Get Ed.
Hi, thank you.
He's supposed to.
Now that you're all drunk, you will enjoy Tom's talk even more. So this Tom he was joining the project pretty early. He also started Cortex, which is one of the long-term storage solutions that we probably talked about here in the room. But we will talk about, I mean, it's slightly related, right? But also not.
Slightly, yeah. Hello, everybody. Nice to be here in Stockholm. We probably want to turn me down on the mic a little bit. Because, thank you, yeah. Hello. So, I'm here to talk about, I'll give you a very quick talk on something called Blazing Fast PromQL. If you see me in the corner fiddling on my laptop, we're actually live streaming this meetup. It's the first time I've ever live streamed everything. I bought like about $100 of equipment off of eBay. And I don't know, so far it seems to work. So fingers crossed this continues to work. It's always interesting trying to get like multiple audios. We were supposed to have another microphone for Bjorn, but it didn't work out. I forgot one adapter. Anyway, the talk today, Blazing Fast PromQL. The talk is not really about Cortex. So I'm just going to give you a very brief introduction because we're going to take one of the pieces of Cortex and see how you can use that to make normal Prometheus very fast. So Cortex is this horizontally scalable, highly available, like clustered version of Prometheus. I started the project about 3 years ago and since then was invited to join the Prometheus team as well, and have worked mostly on the remote write integrations in Prometheus. So if you've ever pointed Prometheus at like an external storage system like Influx or Cortex, that's using code that I wrote up until recently, and then Callum here rewrote it. So Cortex was designed to give you a kind of federated view of all of your different Prometheus clusters in one place. So you could run a kind of global query that said, like, how much memory am I using across all my 15 data centers type thing. It was designed to allow you to have kind of HA without gaps in your graphs. You know, if a single Prometheus node fails, we're replicated, so we can deal with that. And it was designed to store the data for a very long time. So a kind of combination of these features meant, in the Prometheus world, we tend to advise people not to do what we call high cardinality queries. That means if you're doing a Prometheus query that maybe touches more than about 100,000 time series, that's kind of starting to push the limits of what you can do with Prometheus. But if you've got 15 clusters, like we do at Grafana Labs, and you know, you've got 100,000 series per query in each cluster. I mean, a Prometheus can have millions of series, but in one query, you might only want to touch 100,000. But when you've got 15 clusters, you can quite easily write a query that maybe touches 1.5 million series. And then because in Cortex we've got storage going back for years, I mean, the project's been running for 3 years, and we can still read data written 3 years ago. You can see how a combination of those two things mean it's very easy to write slow queries, to write queries that take a lot of time to process. And so this talk is really about how we solved it in Cortex and how you can then use that one component in Cortex with Prometheus to accelerate Prometheus queries. And if the internet is in our favor, and if someone's talking to Brian and asking why, is he putting it back up?
He doesn't know.
He doesn't know. So if we get the server back up, we'll give you a demo at the end. Just to be clear, like Cortex is a CNCF project, just like Prometheus. It was admitted a little bit after Prometheus. It's in the sandbox. It's open source. It's Apache license. So go and use it. Go and try it out and let me know what you think. So over a year ago, about 2 or 3 years ago, we started off with this thing we call the querier. So in Cortex, we've broken Prometheus down into lots of different pieces, lots of different microservices, as is the trend. And we isolate the write path from the read path. So the write path uses distributors and ingesters, and the read path uses these services called queriers. Now they're kind of horizontally scalable, and they're stateless. So if you get slow queries, the idea is you just run more of them, right? Simple. Except for it's not that simple. With most monitoring systems, you don't really have a high concurrent query load. And running multiple queriers is a way of dealing with a high concurrent query load. What you have instead in things like Cortex is you have a low number of very large queries. And these very large queries will just hit a single querier. and sit there, and even worse, they'll sit on a single thread, on a single querier, churning through the samples, producing your aggregated result. So we looked at this, we started optimizing this, and started to think of ways in which we can make this faster. So the first thing, as every good computer scientist will tell you, is we're just going to add some caching. So we added a cache in front of our chunk store, our long-term storage for compressed series data. That cache is really easy because chunks are immutable. Once they're written to the chunk store, they never change. So you can imagine really, really easy to cache. Even better, if two series contain exactly the same data, they get deduped in the chunk store. So we store less of them because they're content addressed, if that means anything. Index is much, much harder to cache because the index has to be constantly updated with new series and new data as it gets added. So this is actually Goutham who gave the first talk. This was his first project when he joined Grafana Labs, was to make the index cacheable. And we had to do all sorts of tricks, and I could honestly give you a whole 20-minute presentation just about how we made the index cacheable, but I'm not going to do that. We then decided it still wasn't fast enough, so we decided what we really want to do, and this was inspired by a project from Comcast called Trickster, is we really want to cache query results. So we really want to, if you execute a query multiple times, we don't want to run the query on the back end multiple times, we just want to give you your old result back. Modulo, evaluating some new data, so you've got a fresh result. At first, we looked at just embedding Trickster. It's written in Go. It's open source, just like Cortex, and we looked at just embedding it, but it wasn't really amenable to like using as a library. So we ended up writing our own thing. And we also had a few other ideas that we wanted to do. So now the rest of the talk, that's really the introduction done, by the way. That's the scene setting. The rest of the talk is really what we did in the query front end. What is this query front end? How does it cache results? How does it make queries faster? And how can you use it yourself? So we've zoomed in on the query front end. The first thing that comes in, this is a Prometheus query, or like a really simple Prometheus query that's just getting the kind of requests per second going into a single job. The first thing we're going to note is that this query doesn't quite align with the step. So to understand what this means, in Prometheus, a range query, and that's a query that produces a squiggly line, produce a graph, right, is actually just a set of instance queries executed one after the other in a very, very simplistic view, right? It's not. We do a lot of optimization. But you can think of these things called instance queries. So if you were to evaluate this, it would tell you what the last 1 minute average rate to that server was. And if you then say, I want this over a span of time, Prometheus will go through every 15 seconds and execute it going back in time from your start time to your end time. Super simple. That gives you the graph. However, anyone paying attention will note that I can ask any random time to any other random time. And that means I'll take my random time, I'll go back 15 seconds, and I'll have another random time. And if I keep doing this, every single one of my queries will be ever so subtly different. I mean, if I have regular spikes in my graphs, those spikes will be slightly misaligned on the graphs that I get. You used to see this in Grafana as your graphs would ever so slightly dance around as your pages were reloading. So we fixed that, by the way, in Grafana just by having those end and start of the queries aligned to the step, which is default 15 seconds. But we did this work before we fixed that in Grafana. So what we did in the query front end is we just aligned the query to the step. This makes the results cacheable, and it also makes the results stable. Well, I guess it makes the results stable, which makes them cacheable. The next trick, and this is where it starts to get fun, is we split the query up into multiple days. So if you send me a 4-day query, I'll split it up into 4 one-day queries. This is where it starts to get cool, in my opinion. It's very interesting in Prometheus, because of this execution model, most of the time you can just do this. Most of these query ranges can just be split up and parallelized. The next thing to note is we'll kind of ignore anything in our cache that's, well, no, I'll get to that in a minute, actually. The other thing to note here is because you've got these points in time that then look back, in this example, 1 minute, if I split them at 24-hour boundaries, actually each query will have to look slightly over that boundary into the next day to calculate its result. And similarly, every boundary. The reason we chose days is somewhat arbitrary, to be honest, but the index that we were reading off was sharded by day. So by splitting by day, we're not actually amplifying, at least not significantly, the load on the index. So we then do a cache lookup on each of these days, because they're now kind of repeatable stable chunks of data, and we see if we've previously executed this query with this step with this time range. We go and look in an external memcache. If we find it, great, done. If we don't, we have to go and ask Prometheus. And then there's one other case, which is, well, we kind of find bits of it. The cache might contain bits of the query that we've previously run, like we ran a 15-minute range here, we ran a 1-hour range here, we don't find the whole day. And so in that case, we have to kind of intersect the two, extract the ranges that are missing, and propagate these in parallel down to your downstream Prometheus or to your Cortex. So for every incoming query, we might break them up into, a bunch of one-day queries. We might find a bunch of cached results and only ask for the last 10 minutes. Or we might, find lots and lots of holes and have to go and ask a whole bunch of queries. And that's what we do. So, have you heard from Brian? But wait, one more thing. We did this about a week ago. Previously, there was quite a lot of coupling between the query front-end in Cortex and the queryers themselves. And we built this model, because Prometheus, I failed to mention at the beginning, Cortex is a multi-tenant system. It's the thing that backs like the products that Grafana Labs sells. But it allows multiple independent users to use the same cluster with complete isolation between those users. And in a system like that, you've got to be really careful that like one user doesn't come along and mash refresh in their browser, issue like 1,000 queries, and just completely denial of service attack the service for every other query, for every other user. So what we do is we queue per user, per tenant, and then we do kind of fair scheduling and some really basic quality of service to make sure that the only person you're denial of service attacking is yourself. So we had to kind of move that to one side, enable the path to go just straight out to a normal Prometheus, and decouple the query front end slightly. So let's see if this works. Let's see if...
So the Wi-Fi is blocking it.
Our Wi-Fi is blocking it.
Yeah, not 1990 port.
Blocking the 1990 port. Can you, do you mind tethering? This might just take a second. We're going to live demos. Oh, don't do that.
Don't do that. Okay, let's not do that.
So,
I'm coming around.
I also don't use a Mac. I don't use Linux because my Mac is doing the streaming. So, if I look really clumsily on screen.
So, there should be a new...
I think we'll just do it for you. What's it called?
Fubat. No, Fubat, yeah.
Connect. I'll let you type it in so the mic doesn't pick it up on Wi-Fi. It's not the same, as your bank account, is it?
It is, but
It
does
is,
that
okay.
matter?
Well.
I thought that's what you do. That's how I remember my
Right then, so Brian Brazil is another one of the Prometheus maintainers. He's based in Ireland and runs a company called Robust Perception. And yes, look at that. So he runs a Prometheus instance that's publicly available on the internet called demo.robustperception. And it's got a lot of data. And so to do this query, we need a lot of data, right? So we're going to take a query. This is basically saying, what is my... Oh, how does keyboard work? This is... you've moved the control button. Yeah, just to throw me off. Thank you. So this query is basically saying, what is my 50th percentile, so my median, query latency to this Prometheus server? That's it, right? So let's go and say, I want to look at Prometheus, and I want to run this query. The query is pasted into there. Everyone can see this okay?
The modern UI.
So we can see that super quick, right? That's up here we see, let's make this a bit bigger for people following along. We can see here this is 121 milliseconds. This is going to make a really rubbish demo if queries are that quick. So we've got a way of making them slow though. We're going to go to the graph. You bet Brian's tuned into the live stream. He's just going to turn his server off right at the right moment to troll me. Don't do it, Brian, please. So I'm just going to... So we have a way of making queries slow, and that is by making them long. So let's just zoom out a bit more so you can see how slow these are getting. Oh, I wish I was on a Mac. So we're up to 6 hours, and it's... how would you deal with a cursor this finicky? There we go. Right, so we're up to 6 hours, and you can see it's taking 500 milliseconds. 12 hours takes 600. Yeah, we really don't like this server, so let's give us a couple of weeks. So it's like 1.4 seconds on 2 weeks. Okay? Now, Cortex doesn't have a UI, I'm afraid. Something I really want to do. So we're going to switch over to Grafana. Ignore the fact I'm wearing a Grafana shirt and we're sponsoring the Meetup and loads of people here work for Grafana. Well, just trust me that, you know, this is all legit. So we're going to add a new data source. Here we go, data sources. And we're going to point it at robust perception, which is here. I'm so clumsy on a Linux machine. Yeah. I should have used your machine to do the streaming, Goutham. Right, so remember, Prometheus 1 is demo.robustperception. And it doesn't work because this is running in a Docker container. No, it's testing still. So how does Docker do wireless tethering?
It does. It shouldn't matter.
Let's try again. Mash that. One. That should say, yeah. How does Docker work? Is there a way to run Grafana not in a Docker container? No, I've not done anything incorrect. Remember, we're being recorded. Right, so here we go. I'm just gonna. How do I apt-get install Grafana?
Yeah, okay, fine. Let's not do that.
Come on. How do I know?
You do the browser. You can do the browser mode. The
Yeah.
queries.
Oh yeah.
Just do the queries from
Oh yeah, that's a good idea. That'll work. Well, it'll work for this. Browser. Save and test. Good,
Yes.
right. So, good save. So let's copy this again. I don't know how I'm going to get that to access the browser to access. No, that's not the right thing. This is so much fun. Copy, paste. Right. So this is accessing. This is now using Grafana, and we're just going to go for 7 days. And we can see here it's a bit hidden. We can see it took 1.6 seconds. Now let's add another data source. Oh, here we go. And this one will access the. So what I've done here is I've run Cortex on this machine, and you can see here it's forwarding to robust perception, and it's acting as a cache. So, is that going to work? Who knows? Localhost. Can Grafana access localhost? No, it can't. Oh, browser, yes. Good. Now, could a browser access localhost? Yeah. How is that allowed? Yep. Well, we'll pretend that's supposed to happen. And now, do we have our history? No, we don't. So, it should be in there. There we go. Right. So, running against Brian's Prometheus for 7 days. There we go. Right. Nope. Accidentally cleared it off. That took 3.9 seconds. It's a bit variable. Now, if Prometheus 2 was the one that was going to run against Cortex, now because this is a fresh Cortex we've just run, we've not issued any queries on it. I mean, I didn't show you that, but you'll just have to trust me. What I'm going to do, what it will do is it will have no hits in the cache. It will only parallelize the query. And I had a big argument with Goutham, good friendly argument, but a big argument with Goutham about whether this would even be any faster, because at the end of the day, we're still hitting the same Prometheus server with the same CPU and the same memory. So here we go. If we click this, this goes to Cortex, runs the same query, and it doesn't work at all. Why doesn't that not work? There's a recording online of me doing this demo and it worked perfectly. It did something.
Yeah, this is good. Can you read on it? But is Cortex running in Docker? Can you read on it?
We're just going to rerun it. Pretend that works. What is wrong? Why does? All right, we'll kill it. No, Cortex is running on my just on this machine. So we rerun it, and we will run this query again. So instance queries works, but range queries don't.
Assume it works.
Yeah. So imagine this worked, and what you saw. Why does that not work? Well, you're not gonna enjoy watching me debug that. Just assume that worked, and I'll edit the stream and paste in the bit where it worked. So no one knows. The end of the day is when this works, when this demo works on laptops that I control. The query run via Cortex with no cache, but with the parallelization, takes about a second. It tends to be 3 or 4 times faster. And that's not a coincidence, right? It's about as fast as the number of days you run it over, modulo a bit of fuzz. And that's because those days are run in parallel, and Prometheus can then use multiple Go routines to process the data. Cortex will merge it and give it back to you. But the pièce de résistance here is that when Cortex's cache now contains the old data, the data you want, the query returns in kind of 100 milliseconds. And so when this works, it's a really convincing demo. You just put it in front of your Prometheus server, you just send your Grafana queries to that, and everything gets faster, and the load on your server goes down, and everyone's happy. So, what are we going to do? We have a bunch of ideas to take this further. We have a bunch of ideas to do parallelization not just in time, but also by series, and therefore starting to take these really big queries, shard them out across multiple workers, and maybe even shard them out over hundreds of workers, process them in parallel, and be able to really crunch huge amounts of data very quickly. We're looking at further integration with Thanos. We're looking at automatic replacement with recording rules, a whole bunch of different ideas. Yeah, that's me. Thank you very much.
Show them docs on how they can use this.
I haven't written them yet. We're going to put a blog post up with how this works in a week or two. In the meantime, the best thing to do is to look at the slides for this, which are online, and give it a try yourself. I think hopefully on a network that doesn't block port 90, and where you don't have to tether, and where it all doesn't go wrong at the last minute. This should be a pretty seamless demo. Yeah. Does anyone have any questions? No? I take that as either you all want to go home, or I explained everything really clearly. Bjorn, go on then. You've got a question. What's he saying on IRC? Is he, I took it down just as Tom ran that query? No, I mean, I've done it before, and it normally is fine. Prometheus has a limit on the number of parallel queries it can execute to prevent this kind of case. But the limit's kind of high. It's like 30 or something.
Yeah, also just use queries. There's also, there's a kind of caching within Prometheus, right? So the blocks that are not being ran will get swapped into ran, so the query might also get faster by just running it repeatedly.
Yes, the raw sample data is cached by the buffer cache in Prometheus in TSDB. But this is caching the results.
I know, yeah. I'm just saying there are caches everywhere.
Yeah. That's why I tend to, in this demo, I run the query twice against Brian's servers to show that it does get faster on its own. Any other questions?
Did I get it right that Prometheus still keeps the whole storage as it usually does? Cortex also saves some part of those data which I queried.
In this demo, Cortex is completely ephemeral. There's a cache for storage, and it's just kept in memory. You can use memcache, or you can keep it in process. But it's not, you can just blow it away, and you can forget about it and bring it back. It's basically stateless. Cortex, at the beginning of the talk, is this big distributed system that will store your data, all your data, and you don't have to store it in Prometheus anymore. And you can store it for years, and you can store lots of it, and you can do parallel queries and all these kind of things. But here we're just focusing on one piece of it, which is the query caching.
So it also could be used as a primary storage for Prometheus.
That's exactly how I use it, right? Exactly how we use it here.
So in this case, you need to configure Prometheus somehow to send data to Cortex.
Exactly, you do. You need to configure Prometheus to send data using something called remote write, which is just in the Prometheus config file, and Callum is one of the guys that works on it. Any more questions? Last question.
So I asked at PromCon as well last year. Is anybody using Prometheus raw as long-term storage?
Yeah, so the question is anyone using just plain old Prometheus as long-term storage? The answer is yes. One of our friends, one of the Prometheus contributors, Richie, has years of data stored in a single Prometheus. And
1.x Prometheus.
oh, an old 1.x Prometheus. Did you say how? Just by setting the retention very high. So, uh-huh. So the statement, not really a question, is that this has been a big problem with Prometheus since the 0.x days. Now, it's not necessarily true, because you've always been able to store data almost indefinitely in Prometheus. There has been, so one of the things has been like, if you have a high degree of series churn, that has always been a problem. But that's not... I'm making general statements, like the churn issue was solved in 2. But in the 1x days, sorry, Bjorn, one sec. In the 1x days, like if you had high churn because it only had a single index, then that could start slowing down queries. And in Richie's case, he doesn't have high churn. He also doesn't have a lot of series in there. He just stores them for a very long time. Does that make sense? Cool. Bjorn.
Churn is always a problem. Like Prometheus saves a single sample in like 1.3 bytes. It's super efficient, but every new metric you have is like a 10 kilobyte overhead or something. And then Prometheus 2 made this twice as efficient essentially. So now you can have twice as much churn as before with the same resources. But there are also other trade-offs.
Yeah.
So at Stockholm we had a not super tiny but very little churn Prometheus server. That was the one that monitored all the other Prometheus servers, where we have like 100 of. And so SoundCloud switched this on very early in the beginning with 0 something, and we had 1 year retention. So after 1 year, we actually hit that retention, and this worked really nice with 1.x because there was so little churn, and it worked actually slightly less good with Prometheus 2. So yeah, it also took a bit more space. But yeah, so if you have a churn, Prometheus 1 has the whole index for the whole time in one big level DB, which is just not performing really well if it gets really big. Prometheus 2 solved that by having like multiple blocks, but then you have many, many blocks in the long-term Prometheus, and this is not infinitely scalable, which is completely differently solved by all those distributed long-term storage database. But like as long as your load is low enough, there is no limit per se. Like it's not impossible to save 10 years of data in Prometheus if the resources are fine.
Right then, I reckon how much time have we got left? Do we want to do one more? How long? Your lightning? That was supposed to be a lightning talk, by the way. 5-minute lightning talk? Yeah. So we'll have Callum for 5 minutes. Yeah. And I don't know whether we can stream this one because we've got to set up another Linux computer.
No, I've shared my slide.
Oh, okay, cool. So, do you want to mute me?
Okay, everybody can hear me, I think? Yeah. Okay, so I'm just going to talk really quick about, as Tom mentioned, I rewrote remote write. So just really quick, remote write is this subsystem of Prometheus that allows you to take all the data that Prometheus is scraping and write it somewhere else, traditionally for long-term storage. Traditionally, Prometheus, we don't really pitch it as long-term storage, even though it kind of can do it based on how good the storage engine is these days and also was in the past. But basically, the system takes all this data and can remote write it somewhere else. So for example, you could remote write it to Influx, Graphite, some other systems as well. There's a big list on the Prometheus website of all of the integrations if you're interested. So really quick, this is the same architecture diagram that Goutham showed earlier. But over here in the Prometheus server, on the left-hand side, we've got this retrieval system, which takes this list of targets that Prometheus wants to scrape metrics from, scrapes the metrics, and then passes them off to the storage layer. And that's important because in remote write, in the past, we used to duplicate all that data, or duplicate some of that data into a buffer, and then batch that data up and send it off to the remote storage. there was this fixed size buffer per scalable thing within Prometheus Remote Write. And if that buffer was full, we would just drop the data, which obviously isn't great for long-term storage if we're just dropping your data before it even gets there, right? The other issue was that we would calculate this number of desired shards, this unit of scaling we had, based on whether the rate of samples that we were scraping versus the rate of samples we were sending was different, and we'd scale up. And so there was a potential to buffer all this data and then get further and further behind, and then scale up and buffer more data and kill your Prometheus. So the idea was we wanted to fix that issue of potentially dropping and then also killing your Prometheus. So how it works now is, as Ganesh mentioned, there's a write-ahead log. We just read the data that we're then going to remote write from the write-ahead log. So the way we fixed not dropping data and not moving your Prometheus was via the write-ahead log. If we're far behind and can't send more data, we just don't read more data into memory that we would then want to send. And we don't scale up if we haven't successfully sent recently, so we're not going to add more buffers that way either. There's one kind of side effect here. When we would scrape data from your targets, we'd get all of the labels that those targets would then have. When we read it from the write-ahead log, per write-ahead log segment, it's just the name of the file. The series labels are only written to that segment once, and then after that, it's just the ID of the series, the timestamp, and the value. So within Prometheus Remote Write, we have to cache the labels. So on the happy path, we're using more memory, but in the worst case scenario, we're using less and not killing your Prometheus, in theory. Could potentially kill your Prometheus still if you're using Kubernetes memory limits like we are, and you start scraping more data and your limits don't match the new data you need. So I seem to like long-living PRs. This was like 6 months of work, thanks to Tom and Goutham and some other people that are not here for reviewing it. And if you're interested in the future, we also, as I mentioned, this sharding, the scaling, need to fix, because we're getting the data in a different way now, the rate isn't exactly the same. And so when Prometheus starts up, it needs to replay this write-ahead log into the in-memory buffer that Ganesh mentioned. I don't know where he went. Oh, right here. So it has to replay all of that data, and then remote write is allowed to start, and it also has to replay that data to do all of that caching of the labels. And while it's replaying that data to know about the labels that it then wants to cache, Prometheus itself is allowed to start writing more data to the write-ahead log. So the sharding calculation, the way it works, is it wants the rate of samples in and the rate of samples out to be the same. It isn't right now accounting very well for getting too far behind and then needing to catch up. So we need to work on that still a bit. If you would like more technical details, there's a blog post on the Grafana blog that I think came out in March, or you could just ask me here or on IRC or Twitter, anything like that. That's it. Thank you. Yeah, question?
So, as you said, you don't really write if by keeping account of the memory or the buffer size, how much is being filled, right? So does that introduce some kind of lag for the output? I mean, whoever viewing that data from that?
Yeah, potentially. So you need to do a bit of tweaking of some config options so that you can scale up to what you would need to scale up to. So for example, you can set the minimum or maximum number of shards you're allowed to have. You can set what the size of that fixed size buffer is. But the idea is that the default should be sane for what most people are running. Yeah.
We normally, in normal operation, everything scales to sub-second propagation. It's not instant, but you shouldn't really notice sub-second.
Yeah.
The thing I like about this, my favorite feature is we had an outage. You can go on our blog and read about it, where Cortex was down for about 15 minutes, and all of the Prometheuses that were writing to Cortex buffered using this write-ahead log. Whereas previously, if we'd had that outage, all of the Prometheuses writing to Cortex would have died.
They would have died or dropped the data.
Died or dropped the data.
Yeah.
And so this meant we had an outage. It was a good one, and no one lost any data.
Yeah. So the write-ahead log keeps these segment files around basically until compaction happens. 3 hours, and then it determines which of those segment files have now been, written to disk instead of need to be in memory. So as long as you're not 3 hours, or if you mess with the config some other amount of time behind, it will always catch up. Yeah. All right. No one else?
Thank you,
Okay.
Callum.
Thank you.